Hey everyone, so this is the intro to our Lab 3 assignment. So for this week, this next 3 weeks actually, what we're going to do is we are going to adjust your robots so that they can run in the maze with reactive and closed loop control. So first, reactive control, we're going to install bumper sensors on your robot if you wish. This part is optional. A bumper sensor is basically just a button set up on your robot in a way that it activates the button when you've hit a wall. So for example, on my bot here, if I were to attach this curved piece in a way that when it hits the wall on the front, if I attach this in some way, you can use hot glue, different types of tape. If I attach the button to the Lego in such a way that when this arm swings, it pushes the button. I don't have any hot glue with me, so it's not going to work perfectly, but something like that. And then your Arduino can tell that you've hit a wall of some sort. So the way this is going to function in the code is you're going to be driving straight some distance, just like we did in Lab 2. But if your robot goes off course, if it's not driving completely straight in the maze, it will sense that when the button is hit, and you can do something to react to that. So that's our reactive control. So for instance, if I'm driving straight, or trying to, and I start pivoting into a wall and I hit it, I can tell the robot to turn in place. I can tell the robot to back up and turn in place and try again, something like that. So now you know when the robot is off course more than 6 inches or so, which is the distance from the center of the maze. So that's reactive control. Closed loop control means that it's going to take encoder readings, which you're going to learn about in lecture this week, and it's going to use them to calculate exactly how much distance it's driven. So in order to drive straight, both the left and right sides have to drive the exact same distance. So you guys tried to calculate that with your motor power controls this last lab, but this time we're going to directly measure it. So we're going to use our brake beam sensors that we covered in lab. So that is an IR emitter paired with an IR receiver. And when the path is blocked, it sends a signal. And then what we're going to do, we're going to attach those to encoder wheels, which we have 3D printed for you in the lab. They are these guys right here. They have 12 holes around the side and a space for a Lego axle. So what your next task is to find a place on your robot that you can attach these to part of your gear train, whether it be the motor axle, your wheel axle, or somewhere in between. I've chosen to apply these on my drive axle for my example bot. So I lengthened these axles here and added those in. And then I've got some kind of tricky Lego business here. Let me give you a closer look. I've attached these that in a way that I can, see, let's use this one here as an example. So I've got my encoder and it's been hot glued to a Lego piece. Some of your encoders might already be hot glued as well. And I'm going to attach it. So I set this up in such a way that the encoder pivots in place until you can center it right on the encoder wheel. And there's certain spots where the wheels will line up with the emitters. You'll have to experiment with that and how your robot is set up. But basically it uses gravity to place it in place. And as the wheel passes through, it's going to count how many holes pass by. And from that, you can calculate that either one rotation has passed. One rotation is 12 12 holes is one rotation, which is also one rotation of your wheel, which has a certain diameter. So one rotation of your encoder wheel means one circumference has been driven. And you're going to use those properties in your code to calculate distance based on encoder counts. So the first part of that, after you figured out your mechanical design, I wouldn't attach them just yet because circuitry is a bit more finicky with this lab than the previous ones. So I have set up just a little testing right here. It's got an encoder on an axle, and I would try and build something similar to that, and make sure you have your wiring correct on your encoder. So when you fully plug it in, the default value should be 0. And when it's the path is empty between the emitter and the receiver. And I want you to open up the digital read file, which is pretty basic file here. Let me show you. So the digital read is a basic Arduino file. It's actually included for you. If it will load. So as we get to that, the wiring for this lab, I'm not going to give to you directly. It's your job to find it from this diagram and the lecture based on the data sheet, which will be provided to you as well. This is a common sensor data sheet. We've given you this, we've given you the circuit diagram, and from that, you guys should have to figure out the wiring for yourselves. So once you get that done, you're going to go to File, Examples, Basic, Digital Read. And once you get this open, you'll have to change it to a pull-up button, which is how this sensor works, just like our regular push buttons. Pull up to, and then if I plug in an Arduino, select our COM port, that's good, and upload. Compiling, uploading. I am setting up the wiring down here, but like I said, I'm not going to show you because that's your job. Cool, done uploading. If I now have this hooked up correctly, we can see that the default is 0. And then if I put this up to my rig here, I'm going to spin the wheel and we should see the values change back and forth. So if we were to count 12 of these, so here we're at 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be 1 full rotation. So that is the bare minimum of this encoder. But what we're going to use is called an interrupt to help count those for us, so we don't have to deal with that directly. So in order for that to work, you're going to have to go in your lab assignment. It shows you down here the pin change interrupt. You'll have to come over here and it's going to send you to GitHub instead. That's fine. You're going to go ahead and download. Cool. Put that somewhere you'll remember just for now. And then it depends on your setup. Your Arduino might be storing somewhere else, but mine is going to document/Arduino. So I'm going to my file explorer. I'm going to find that, documents, Arduino. And then this is all of the libraries that I have installed. So what you're going to do is you're going to find where you just downloaded that. You're going to extract it into this folder. So I just copied that address, putting it here, and I'm going to extract. Cool. And now we have pin change int that is here. And this is all that's included in the library. We don't really care what's going on inside of that, just that we can use it properly. And now when we restart Arduino, it will have included that library. And we can tell it's included because if we scroll down here, contributed libraries that we've downloaded includes pin change int. So what that does is with these codes that we have included with your starter code here, it's going to attach the pin. First we set it to input pull-up, just like we did in digital serial read. But now we're going to attach it to an interrupt. So this is our pin name. It's in our definitions above. But it's going to count every time that value changes. And then it's going to run this function. And here is the function that we've attached it to. So every time that that pin changes, because we are spinning our wheel, it's going to call this function. And this is a shortcut that says increase that variable by 1. So left encoder count. How many clicks, how many rotations has the left wheel done? And we're going to use that count in our controls. Now that we know how that works, let me show you the rest of the code. So we have pin change int as a library, which allows us to use this attach interrupt function. That's everything we just downloaded. Then we have the typical variables that we've been using this semester, defining your motors and stuff like that. Next, we have a couple new constants. Encoder counts per revolution is 12. We've just talked about that. There are 12 holes in one wheel. Next is the distance per revolution, which is your wheel circumference, and the degrees per revolution. This is something that you'll have to find by experimentation, but it's asking when you run the wheels in opposite directions, how many degrees does your robot turn in place based on one encoder count? And then we have, these are just defined words, just like we used in Lab 2, so we can build our array. And here are the 2 pins that I've chosen to use as my encoder digital inputs. Those can change whatever you would like to use. And then, let's see here. Yes. Besides our normal start push button, that's where you would add more buttons if you'd like to use the reactive control. So if you want to have a bumper sensor, you'd define more push button names. Let's see here. Gain. Gain is having to do with the drive function. So we're using our encoder counts to implement a proportional drive control, which means as we get closer to our goal, we're going to slow down, just like you brake as you're coming up to a stoplight. We want to use this number to find the speed we start at. So if we are 100 encoder counts away from our goal, how fast do we really want to go to catch up to our, to minimize our error, which is currently 100 clicks. So in this case, I've chosen gains of 5, which means that for every encoder count we have in our error, I'm going to multiply that by 5 as my PWM setting. But we do have a maximum of that. It maxes out at 255. So eventually we're going to get below 255, which would be less than an error of about 50 clicks. And then we're going to start slowing down from max power. And then we need a distance tolerance because we're never going to get exactly 0 error on both motors. So just having something small there helps bring the code along. Deadband we've talked about. In Lab 1, it was that smallest PWM setting that didn't let your motor go at all. This is so when we're using our proportional control, if our error is still too big, we don't want to go below this number where our motor won't even run. This is going to be a different number from your lab 1 because you've added more weight from your robot itself, and it might be different per motor. So experiment with that. Find the minimum power that your robot will drive on a surface. It can't just be in air because that's a different force than on a table or something like that. Here we have our global variables. These are unsigned, which means that they're always positive. They're integers, which means they're always a whole number, and they're volatile, which basically just means that they can be changed outside of the main functions. And we initialize those to 0. And then moves is where you will create your moves list. So I've given you the shape of the maze in the procedure document. It's up to you to find out the moves list. Each square is 25 centimeters, 12 inches. And that's how you'll build your array, just like we did in lab 2. Here's the setup function. We're starting serial communication so we can have test statements. We're running the motor setup, input pull-up. If you added more buttons, you're going to have a pin mode statements for those too, putting them to input pull-up. This is all provided for you, but this is attaching the left and right encoder pins to their respective functions, which will do the counting for us. In our main loop, we're going to wait for that first push button, and then we're going to iterate through our moves list. It's up to you how to call your functions correctly when you want to move left, right, or forward. And after it's done that move, it's going to turn the motors off and wait a second, and then it's going to do the next move. Some functions that I've provided for you is the start of a drive function, some variables you'll need. You'll have to figure out the counts desired based on this input distance, and then the definitions we did earlier about encoder counts and distance per revolution. So you'll find those equations in your lectures, and you'll have to build those yourselves. We reinitialize the encoder count because every time we start a new move, we're going to zero that encoder count out so we can count correctly. In order to enter our loop, we need our current error to be just a little bigger than our tolerance, and then we'll update that correctly later. So here is our while loop for the proportional drive. We're going to keep driving until we reach our goal or near enough to our goal. So while our error on either side is bigger than our tolerance, we're going to find the new PWM. I'll tell you in a second how you're going to fill in that line of code. But basically, we're going to calculate that somehow, and then we're going to execute that new speed, and then we're going to update the error. So between here and the next loop that it comes through, the error should have updated because we are counting our changes in the pin in the meantime. So that happens outside of the code. That's why it's called an interrupt. Whenever it happens, it'll interrupt your code, update the variable, and then go back to where it was, which is very helpful and very speedy. And then if you'd like to implement the reactive control, you'd add your code here for that. And then it just keeps going until that certain step is finished, until you've reached near enough your goal. And then it's going to return to wherever you called it. And then you'll have to copy that for some sort of turn function. Here you'll write a reactive function if you want to use that. Here's where I was talking about earlier, how we'll calculate our new PWM. So we're going to give it the gain. What's the proportion of error to speed that we want? The deadband for that motor, and the current error. So if error is within our tolerance, then we can shut the motor off. Our return is 0. Otherwise, we want it proportional. So we have a high error, we're going to have our constant gain, we're going to have a high command direction. If we have a low error with our constant gain, it's going to give us a lower command. And then we're going to constrain it, which is bounding it within the minimum of deadband and the maximum of 255, because that's the only settings we can give our motor. And then I've actually forgotten a line here. So if you guys want to implement that on your downloads, we're going to return command direction. Cool. And then we're all the way at the bottom, and those are encoder counts. So this is the starter code for this lab. Like I said, there's quite a bit for you to fill in. I've also provided an example of reactive control. So if you want to, let's see here. This is from previous semesters. We used to have a whole lab where we would drive the robot with just the buttons, but we felt for this time that it's a bit repetitive and a lot of work. So for this time, we've combined them into the two labs. So here's an example. We have our definitions. We have a milliseconds per degree. If we were turning, we would need that because this one doesn't use the encoders, it's just the buttons. Here we have our bumpers. We can actually define full functions if we want to. Like this one is a function, digital read the left bumper pin. Here is our button pull-ups. And this code, if you'd like to implement it, what it does, it's driving forward until your regular button press, so the start and go button. It's going to drive forward until you hit the stop button. But while it's doing that, if it senses a wall, it's going to jerk away. So if left touch calls that pin, if it's low, if it's low, that means a button has been pushed. Oh wait, no, that was correct. Okay, so this is an empty while loop. While no buttons have been pushed, it's going to keep driving forward. As soon as a bumper is activated, it's going to jump out of this loop. And it's going to find was it the left or is it the right? If it was the left, so if you're driving forward and your bot is hit on its left, which means you're driving too far that way. In order to correct it, you want to turn right. So here, left bump, turn -30. I've chosen negatives left just from like the unit circle. So if it's hit on the left, it's going to turn right and then keep driving forward. Same thing, vice versa. If it's hit on the right, it's going to jerk left and continue driving forward. So that's a pretty basic example of reactive control, but we wrote this out for you if you'd like to implement it, just so you have something to go off of.
All right, that's about everything you should need to know for this lab. Please let me know if you're having troubles, if you have any questions in class. Be sure to do your pre-lab, and I'll see you guys on Friday.